All right, welcome back to Chem 150. Today we're talking about Chapter 12 in the Denniston book. This is a chapter on the first real functional group we're talking about, which is the hydroxyl group. And so let's see. So we probably are used to seeing the hydroxyl group in the form of sodium hydroxide. And we learned that that was a strong base in general chemistry, that it completely dissociates into sodium ions and hydroxide ions in water. But what's going to be different about the hydroxyl group that we're going to be talking about is that it's going to be attached to other nonmetals and mostly carbon. So when we look at a group like, let's do it this way. Let's look at a structural formula. So we have OH attached to the carbon. So this is a non-metal hydroxide, and we would call this an alcohol. And what's so special about an alcohol is that you have the non-polar part of the compound. Here we'll do ethanol. And then you have the polar part of the compound. And I'm going to draw this as an angle just to emphasize something here. That remember when we talked about polarity in Chemistry 140, that it's the unequal sharing of electrons between two elements, and that oxygen is more electronegative than hydrogen. Remember, electronegativity is the ability of one atom to pull electrons away from another atom, and electronegativity increases as we go across the periodic table up to group 17. Remember, the group 18 does not have an electronegative value because it doesn't want to accept an extra electron. And then electronegativity decreases as we go from top to bottom because we're getting further and further from the electropositive nucleus. So increases as we go across and decreases as we go from top to bottom on the periodic table. So, and remember, hydrogen's a little tricky. Hydrogen electronegativity is 2.1. It's almost like carbon at 2.5. So hydrogen is a nonmetal, and its electronegativity is closer to carbons than it is the metals that are in group 1. All right. So oxygen being further over than hydrogen is more electronegative than hydrogen. So that means there's an unequal sharing of electrons between the oxygen and the hydrogen. The electrons over time spend more time around the oxygen than the hydrogen. And so we get a partially negative charge on the oxygen, a partially positive charge on the hydrogen. Well, and that creates a polar bond here. Sometimes we draw that as an arrow with pointing towards the more electronegative element. It's a force here. Remember, chemical bond is a force that holds these two elements, oxygen and hydrogen, together. And the force is moving towards the oxygen because the electrons are spending more time around the oxygen than the hydrogen. So because this part is polar, this part will dissolve in water. Remember the phrase, like dissolves like. Polar molecules will dissolve in polar liquids. And so water being a polar molecule, in fact, a lot of people, when they talk about alcohols, they like to talk about in terms of it's a lot like water, right? You've got oxygen, and in water you'd have a hydrogen down here, and you'd have a hydrogen down here, and you'd have a lone pair up here, and a lone pair up here. Remember the Lewis structure, the SEPR theory for water. And again, these are partially positive. This is partially negative. And the angle between the hydrogen, oxygen, hydrogen is 104.5 degrees. We'll just say 104 degrees here, something like that. And so that if we look at an alcohol, look at the difference. You have a methyl group. It's attached to the oxygen, and then we're attached to the hydrogen. Same thing, about 104 degrees here. Same thing, there's 2 lone pairs on this oxygen up here. So they look a lot alike. It's just that we've replaced one of the hydrogens with an alkyl group, so we'll put an R here. Now that could be an alkyl group or an aryl group. Remember, aryl group is like a benzene ring, phenol group. All right, so alcohol, in this case, this is ethanol. Ethanol would be soluble in water. Now, the book talks about as this chain of the alkyl group gets longer, the alcohol doesn't dissolve as well in water. All right, so that makes sense. This is a nonpolar group, right? And so as this chain gets longer and longer, the nonpolar part of the molecule influences the solubility of this nonpolar part into polar water. So as the chain gets longer, the alcohol becomes less soluble. So what kind of alcohols are there? Well, we've seen ethanol, and we have seen something like this. All right. So what would you call this compound? Well, it's 3 carbons long, so that starts with a pro. Maybe if you go back to the alkane, it'd be propane, but this is an alcohol, so we would say propanol. All right. Now, this hydroxyl group could be attached to the center carbon, so we would get something like all right, so what's the name of this compound? This would be 2-propanol. 2-propanol. Okay. So these would have different chemical and physical properties. This is called propanol is called a primary alcohol, and sometimes we just do it like that, 1 degree. All right. Because this carbon is attached to only one other carbon. This carbon is attached to only one other carbon. All right. In the second alcohol, the carbon is attached, this carbon that is attached to the hydroxyl group is attached to 2 other carbons. So this would be a secondary alcohol. All right. You can have an alcohol like, let's see if I can, let's just go to the next slide. You can have it where the carbon is attached to 3 other carbons. So you have a carbon here, maybe a CH3. Let's say it's another methyl group up here. Another methyl group here. And now we have the hydroxyl group here. All right, so what would be the name of this alcohol? Well, the longest chain is 3 carbons, 1, 2, 3, or 1, 2, 3, or 1, 2, 3 up here. So the longest chain is 3. So it's still propanol. And you would say 2-methyl propanol. 2-methyl propanol. And this would be, oops, yeah, I've got to add the alcohol because the alcohol is not a primary alcohol, so let's fix that. This would be 2-methyl 2-propanol. All right, 2-methyl 2-propanol. And again, you go, why is that? Well, again, longest chain is 3 carbons. But we do have to tell the person where this our hydroxyl group is. It's on the second carbon, and so is the methyl group. So 2-methyl 2-propanol, and this would be a tertiary, or that's the way we would say it. This is a tertiary alcohol because the carbon that is attached to the hydroxyl group is attached to 3 other carbons. So, what are we going to be doing? Well, we're going to be talking about all different types of alcohols, and the general form is just ROH, where this is the alkyl group. We're going to be talking about phenols, which we mentioned in the last chapter with the aromatics, that you have a aromatic benzene ring, and attached to that ring is the hydroxyl group, and we could draw it something like this. That's going to lead into ethers, which look like this. It's an alkyl group, single bonded to an oxygen, single bonded to another alkyl group. So again, all of these things, if you want to think of them, they're all looking a lot like water. It's just we're substituting the hydrogens with alkyl groups. And then we're going to get into another class of compounds, and it's funny that they're mentioned here, but they should be, because when we look in the periodic table, we have oxygen in group 16, and right below it is sulfur. And we know from Chem 140 that elements that are in the same group have similar chemical properties. So what happens if we swap out the oxygen and make this an alkyl group with sulfur and hydrogen instead of oxygen and hydrogen? Well, this becomes a thiol. All right. So there are big differences here, and here's where the big difference lies between the alcohols up here and the. And actually, I probably should kind of make a dashed line between ethers and alcohols and water. Up here, the thing that's really different than let's say this is category 1, category 2, and category 3. What really makes first category different than the other 2 categories is hydrogen bonding. You definitely want to take note of that. Oops. Now, hydrogen bonding is not a true bond. And we talked about this again in general chemistry. Hydrogen bonding occurs when hydrogen is bonded to nitrogen, oxygen, or fluorine. And what it is nitrogen, oxygen, fluorine are so electronegative. Again, what happens here is, let's change the color just to show you what looks the difference here. So here's a water molecule, and we said this was partially positive on the hydrogens, partially negative on the oxygen. Oops, positive, yeah. All right, so yeah, that's not the best, is it? Let's do this again. Partially positive, partially negative. All right, so when another water molecule is in close proximity, this hydrogen will be attracted to the oxygen of another water molecule, because the water's the oxygen's partially negative and these hydrogens are partially positive. And this linkage can occur over and over again. We could have another water molecule here. This hydrogen could be attracted to it. This hydrogen could be attracted to it. And then we'd have the bond here between the actual bond between the oxygen and hydrogen. And remember, it's these voids in an ice that causes ice to be less dense as a solid than it is as a liquid, which is kind of unheard of. I mean, it's very strange for the solid to be less dense than the liquid, but that's what happens with water because of this hydrogen bonding. So these dots represent hydrogen bonding. It is a strong force of attraction between the hydrogen of one molecule and the oxygen of another molecule. So we'd have one here, we have one here, we could have one here. So, why is that so important? Well, the alcohols have this hydrogen bonding, and they're going to have much higher boiling points and melting points than category 2 or category 3 that does not have the hydrogen bonding. So there are some distinctive differences between alcohols, ethers, and thiols. And we're going to first focus on the alcohols, but the reason why we bring these all up, all three categories up in this chapter, is that they all kind of trace their roots back to compounds like water. All right. Now, I will say that when we're dealing with alcohols, let's name a couple of alcohols here. Let's next slide. So let's say I have. Let's do something like this. Yeah, I need to. Yeah, let's erase. I need to erase one of these hydrogens here. Probably should have just picked one out of the book. All right, so we have something like this. All right, so let's name this compound. All right, so first of all, when you're looking at it, look at the longest chain. So 1, 2, 3. So 1, 2, 3, 4, 5 carbons long. So we know we're dealing with pentanol. All right. Now, here's where we have a problem. The bromine is on, right now, the second carbon, and the hydroxyl group is on the fourth carbon. So which one takes precedence? The hydroxyl group or the bromo group? Well, the hydroxyl group takes precedence. So this is going to be carbon 1, this is going to be carbon 2, this is going to be carbon 3, this is 4, and this is 5. So just like the double bond takes precedence with the enes, the alkenes, or even the triple bond that we saw in the last chapter, in this chapter the hydroxyl group is going to take precedence over the halide group. All right, so we would name this substance choose a number, Brent. 4-bromo dash 2 dash pentanol. Why the 2? Because you have to tell the person that this alcohol, the hydroxyl group, is on the second alcohol. I mean, on the second carbon. If you put, it could be on the primary. It could be on the, the primary or the end carbon here. And so you would have 4-bromo 1-pentanol. So you do have to put the 2 in here to tell people where the hydroxyl group is. Some really important alcohols have their own names. We've seen this one before, the 2-propanol, and it looks like this, 2-propanol. You probably don't know it as 2-propanol. You know it as isopropyl alcohol. All right. Other important alcohols are going to be, again, methanol, especially in the state of Kentucky, bourbon capital of the world. Ethanol. And then we also have, this one's a really strange one, but this is a really important one too. It's a diol. It's got two OH groups. So it's it starts out as an ethyl group, like ethane, and we've knocked off a hydrogen off each end and put a hydroxyl group. So we get this. And this is called 1, 2 ethane diol. All right. So notice this. This is the first time we've seen this diol. We have two hydroxyl groups. That's why we have the 1 and 2 here, because again, both hydroxyl groups could have been off one carbon. So we have to say 1, 2. The carbon backbone is ethane. So 1, 2 ethane diol. But most people don't know it as this. They know it as ethylene glycol. And where is ethylene glycol used? Well, this is a substance in antifreeze. Now, something interesting about this is that these hydroxyl groups, when we taste the hydroxyl group, it's sweet. So ethylene glycol is very sweet because it's a small carbon chain with these two hydroxyl groups on it. And so this is why it's always a concern around pets, animals, that they ingest this because it tastes sweet, but it's very toxic to the body. Okay, so 1, 2 ethane diol is the IUPAC name, and I like that name. I think it's important, but there's also a common name, and you're going to need to know these common names as well, because you definitely know isopropyl alcohol. You've heard it more so than 2-propanol. And ethanol, you may have heard it called this. I mean, the common name would just be ethyl alcohol. So you just have to be, it'd be nice if we just stuck with one name, but we know in reality that these are more spoken names for these compounds than their IUPAC name. All right, so how do we make alcohols? Well, we make them from sugars. So just like we're making bourbon, we take some sugar, usually from grain sugar, and we add yeast to it. And your book says enzyme reaction. Well, that's a yeast enzyme. All right. It doesn't have to be yeast. I mean, there are different ways to make alcohol. In fact, there's a cracking process that's it's probably the cheapest way to make like ethyl alcohol. But the problem is it sometimes leaves traces of benzene in it, and we don't want to drink benzene. So there's a law that says if it's consumable alcohol, it has to be made from natural grains. So or grapes. It's something like, it has to be a natural fermentation process. So when we put this enzyme in here, we get ethanol. And carbon dioxide's given off. So if you've ever toured one of the bourbon distilleries when they're got the batch process and you see it bubbling, this is an exothermic reaction. It feels warm in that room, and carbon dioxide's given off, and they're making the alcohol, and then they're going to distill that alcohol off. And they talk about, with wine it's around 12%, 12 to 13%, and that no distillation required. It's about 12 or 13%. That's about as much as we're going to get that way. With bourbon, you have to distill it. When you distill it, you get somewhere around 40 to 85% alcohol. 40% to 85%. All right. Another important alcohol looks like this. You take a propane chain, Oops, I need to take this one out. And you get and you attach a hydroxyl group to each one of the carbons like so. So this substance is going to be sweet. I remember my professor tasting this in the lab, and I just didn't want to have anything to do with it. But he said, "Oh, it tastes very sweet." This is called glycerol. Problem is, you don't know what's been in that glycerol in the lab, so you should never taste something in the lab. But again, this is old school lab glycerol. All right, so that's the common name, glycerol. You'll see it in soaps. You'll see it in shampoos. It's a kind of a sticky, sticky kind of substance. We used it to lubricate the glass rods that we were going to put through a rubber stopper. That's what it was commonly used for in the lab. So that's the common name, glycerol. What would you name it for the IUPAC name? Well, you look at the long chain, it starts out as I always think back to the alkane, propane. This is propane. And then you've got 3 hydroxyl groups. So it's not a diol, it's a triol. Propane triol. And so then you'd have to say 1, 2, 3 dash propane triol. Another thing that's kind of interesting about this is that, sugars. Let's talk about sugars a little bit. Since we've seen all these hydroxyl groups and we've been talking about, the hydroxyl group is sweet, so what does glucose look like? Well, glucose, you'd have a 6-carbon chain. And let's look at some of these other carbons first. These are the ones I want to focus on. So this one has a hydroxyl group. All right. And then we'll alternate the hydroxyl group to this side. And you say, why are you doing that? Well, if you put all the hydroxyl groups on one side, it does create some repulsion. I mean, this thing takes up space. So that's just typically what we do in fashion, is we'll alternate. You could write them all on the same side. It's just that it gets to be practice where, and we could do that. Here it is. It just gets to be practice where you put them alternating. All right. And so then down here at the end, you'd have another hydrogen, another OH, and then a hydrogen coming off like that. Now, that's what we generally think of as sugars. And again, it's these hydroxyl groups that makes this very sweet. This is glucose. Now, here's where the tricky part is. Up here on this carbon, it's actually a carbonyl group. It's double bonded to an oxygen here and then a hydrogen here. And you go, well, is there other sugars? Yeah, this is glucose. All right, they call it D-glucose. If we said, okay, I don't want to write that. I want to write CH2OH up at the top, kind of like we did down here. That's what this is. This group down here is C2OH. We're going to do that at the top, and then we're going to take the carbon down a notch and then put the double bond. And then go down here and make it a total of 6 carbons long. And then here I'm going to put an OH group and a hydrogen and an OH group and a hydrogen and an OH group and a hydrogen, and then end it just like we did here. I'm just going to write it this way, C2OH. That's fructose. Fructose. And just, let's see, I'm running out of space here. Let's see, what do I want to do? I'm going to just alternate. I'm going to alter this first one we did, the glucose. Let me erase this and erase that. Okay, now watch what happens here. Instead of having this carbonyl group, which made those sugars, glucose and fructose, I'm going to take the carbonyl group out and I'm going to make it all like this. No carbonyl group. Well, this becomes an alcoholic sugar. This particular one is called sorbitol. Alcoholic sugar. So you see these alcoholic sugars, they're sugar-free, they're in sugar-free gum. Some of them talk about being the sorbitol. It's again, it's used in gum a lot because when it dissolves, it actually has a cooling effect. So they like to put sorbitol in like your dentine ice or something like that, so that when you get that mint flavor, but you also get this cooling effect. Again, some diets, they say stay away from the sugar. They'll have you ingest sorbitol. We don't digest it the same way, and we generally don't have as many we get as many calories out of these alcoholic sugars. So that's another thing. So we had glucose, fructose, now we have sorbitol. All right, let's talk about some chemical reactions with alcohols. And they generally are an oxidation reaction. All right, so let's talk about what we've seen before. We've actually seen this reaction. Let me change this to another slide. All right, so in the previous chapter when we were talking about alkenes, which is double bonded carbon, we could add that to that water, and again they showed it something like this, and we get an addition reaction. Because this opens up, and you got to have a strong acid here, strong acid as your catalyst. This opens up the double bond, and you get a hydrogen, a carbon, a hydrogen here, and the hydrogen here, and then you get the double bond opening, the hydroxyl group goes here, and the hydrogens here. So this is called an addition reaction. Now, they get a little more sophisticated about this addition reaction in this chapter. They want to talk about it in terms of oxidation and reduction. It's an oxidation reaction. So here's what you need to know. A reduction reaction in organic chemistry especially, this is the way it is talked about, but a reduction reaction, I'll just say RXN for reaction, means the loss of oxygen. Loss of oxygen. Or it can also mean the gain of hydrogen. All right, so looking at this reaction up here, would you call this an oxidation reaction or a reduction reaction? Well, we gained oxygen in this reaction, so this would be an oxidation. Oxidation reaction. You know, where you see this, and maybe it's coming up in one of another when we talk about some of the carboxylic acids and fatty acids. That'll be in another chapter. But this oxidation, a lot of times, like you'll have this, you'll have an alkene, and this alkene will be a long chain carbon with some double bonds in it. That makes an unsaturated hydrocarbon, and that makes it like an oil, like vegetable oil. Well, over time, it becomes oxidized. These double bonds open up, and the oxidation of that oil makes it rancid, makes it smell, stink, So I'm sure that's coming up later. But here we're talking about, yeah, the oxidation of an alkene into an alcohol. We can also make alcohol by a reduction process. So let's see that process. So in this process, we have, in this case, I'm going to use an aldehyde. All right. And I'm going to add to it hydrogen. And then I'm going to have a catalyst for that. And what's going to happen is that double bond is going to open up, and we're going to get a hydroxyl group here, and a hydrogen here, and a hydrogen here, and a hydrogen here. So here we're adding, the oxygen was already present. So we're not gaining an oxygen. We are adding a hydrogen here and here. So this is a reduction process. This is a reduction. Okay. And we have gone from an aldehyde with the carbonyl group. This is the carbonyl group that you need to recognize. We've gone from a carbonyl group to a primary alcohol. The alcohol is attached to the end carbon here. I guess I should maybe made this like ethanol or something, or a ketone. Like we could have done this. Let's do this. Let's do all right, so here we have 1, 2, 3, 4 carbons long, so that's butane. But because this is a ketone, this is an alkyl group with a hydrogen. Or oops, this is an aldehyde too. No, it's ketone if this would be another alkyl group. This is butanol. Oops, with the U there. So butanol added to hydrogen gives us the primary alcohol, butanol. All right. To make a secondary alcohol, so this is primary alcohol. Carbon, it's only attached to another carbon. Here's the oxygen. To make a secondary alcohol, we would use a ketone. So here's what a ketone looks like. We could have something like this. All right, so this is a ketone. What makes it a ketone? It looks kind of like the aldehyde, but over here, instead of having a hydrogen, we have another alkyl group, ethyl group. So this would be pentanone. All right. And so again, we'd add hydrogen. Double bond would open up. And we would get this, which would be 3-pentanol. 3-pentanol. So this would be a secondary alcohol, because you have, here's the oxygen attached to the carbon, but this carbon's attached to 2 other carbons. So This would be a secondary alcohol. All right, next type of reaction. Let's just move to another slide so we know that we're talking about something different here. Here is the dehydration of an alcohol. So here, the other ones were addition reactions. Now we're going to take an alcohol, and I'll take the general form R, C, maybe another C, and then water's here. So this is what we want to show. There's a hydrogen here and a hydroxyl group here, and a hydrogen here, and then on this end we could have another hydrogen. All right, so how do you dehydrate something? Well, in chemistry, the way we generally do it is we use a strong acid, and we use heat, which I want to show it as a delta symbol. Your book actually spells out the word heat, but I'm going to use a delta symbol to represent heat. So the other one, we had hydrogen and a catalyst. Here we have the hydrogen ion, a strong acid. And what it's going to do is it's going to act as a catalyst to collapse, to remove the hydrogen and hydroxide. So that's why we call it a dehydration reaction. So we get water over here. And then the bond here between the carbons becomes a double bond, like so. So we've been talking about ethane or ethanol. So here's ethanol. All right, and we can put the hydrogens in if you want to. So we add acid, and this is really important that you, I think this is what I kind of remember from organic. The main thing here is that you've got to know what you're reacting it with. It can't, I mean, sometimes people forget this part of it because it's over the arrow. But if you don't have the strong acid and the heat, this reaction does not happen. So these are important substances. It's just that they're not consumed in the reaction. And so just make sure that you write that down, that you know that it has to have a strong acid and heat for this dehydration to occur. But what happens here is that double bond forms, and we go back to an ethene that we've seen before. And then always, because it's a dehydration reaction, water as a product. You're removing water from the substance. I don't know if you've ever seen the reaction where you take sugar and pour strong, you pour strong like sulfuric acid, and it makes a big black cone. Miss Lenning, it teaches the Chem 140. She's does that demonstration sometimes, and it's the removal. So you have sugars which have lots of hydroxyl groups and hydrogens, and you're removing this from that long chain of sugar, and that's why you see this cloud being formed. It's actually steam being condensed into water vapor, and it's a dehydration reaction. And you generally don't have to apply heat directly to the reaction because the reaction generates so much heat, it's self-generating. The heat comes out and actually creates the reaction. All right, let's look at one more reaction, and then let's see. I think I'll call this. I'd say we're getting. Let's do one more reaction. We'll call this a video. Last one I want to talk about is a true oxidation reaction with alcohol. So you have an alcohol. name the alcohol. All right. So with this alcohol, we are going to add an oxidizing agent. And so that's why you'll see this symbol. All right, oxidizing agent. Now, that oxidizing agent, the most commonly ones used in organic chemistry is this substance. And another one, which we try not to use as much, is the chromic acid. All right, so this is chromic acid, carcinogenic. The potassium permanganate is a real purple solution. We generally mix that with some base. All right, so these are fairly strong oxidizing agents. And you go, why do we use oxidizing agents? It's a great way to, well, assist in chemical reactions, but generally oxidizing agents tend to tear organic substances apart. And so that's what's going to happen. It's going to change. Let's do this. It changes the organic substance. That's what's going to happen here. We have methanol. We add a strong oxidizing agent, and it actually causes the loss of hydrogen. And we get this substance, and usually water. That's where the loss of the hydrogen goes. It goes out here and forms water. So recall that oxidation is the gaining. Oh, well, let's not say it that way. That's not the way I thought. When we went back a couple of slides, let's go back a couple of slides. Reduction is loss of oxygen or gain of hydrogen. So that's a reduction. Loss of oxygen, gain of hydrogen. So here if reduction is loss of oxygen, oxidation is gain of oxygen or loss of hydrogen. Oxidation, gain of oxygen. Well, we didn't gain any oxygen. It's still one oxygen. But we did lose a hydrogen. We lost this hydrogen here. And we lost this hydrogen here to form the two hydrogens required to make water. So we lost two hydrogens. So this is an oxidation reaction. So that's going to be critical when you're doing this chapter, is that you can see, let's say they give you the reaction, they give you this entire reaction, that you can see, oh yeah, I lost two hydrogens on this alcohol, and because I lost two hydrogens, that's going to be an oxidation reaction. All right, that's where we'll stop at today, and we'll pick up this later this week. All right. Thank you very much.